Okay, so today I will go more in the detail of the algorithm to solve the MHD equations, and so I will describe. I will put more emphasis on what is done in RAMSES, but most of the codes are using similar methods. So in principle, I hope it will go beyond just describing what is in RAMSES, and I hope to help you to get some background that will be useful in the different contexts. Right. So the plan of actually that's 2 lectures, so today and tomorrow, and so will be the following. So first I will discuss a little bit the stability issue of the equations, which come from the discretization, as we will see. Then I will spend some time to actually discuss a little bit the MHD equations, the standard and conservative forms, including the MHD waves. And the reason is that, as you will see, the numerical methods are actually deeply rooted in the physics of MHD. So it's important to understand what's going on there. Okay. Then the Godunov methods and the Riemann problems. And then I will spend some time describing a different class of solvers, in particular the so-called row solver, which is a linearized solver, and then the HLL type of solver. And I will finish with the so-called HLLD solver. As you will see, there are quite a few steps, so I don't know, maybe it will not be extremely easy for you to follow. So maybe you will need to look at the slide again. I think it's useful to see this process at least once, because HLLD is really the solver that tend to be used by most or developed in most codes, because this is the most accurate solver we have at the moment. And it's always good to know exactly what you are doing and not use things as black box. So that's the goal of that part. So I suspect I will probably finish here today. I'm not sure exactly where, depending on how fast I will be. And then I will discuss the issue of high order schemes, second order schemes in this case. So how we go from first order to second order, the so-called Messel-Koch procedure, and the issue is the slope reconstruction. Quickly, maybe some 1D and 2D tests, and say some word on comparing the solvers. And then I will address this important questions of a multi-D MHD, and what is specific to this MHD or today's MHD equations. Unlike in the hydro case, so in hydro essentially when you have a 1D problem, you can easily go to 3D. Okay, you just have to repeat the same procedure in 3 directions. As you will see, things are more difficult in MHD because of the DV constraints. There is a difference, fundamental difference between 1D MHD and 2D MHD. Okay, then between 2D and 3D, it's essentially the same thing. But when you go to 2D, then you have to be very careful with DV, and that's introduced. A couple of methods have been developed. So I will discuss that. Okay, so let's start. Okay, so let's start with a very simple equation. So the so-called advection equation, where you have just a sort of you have replaced the velocity by just a constant, and so you want to solve this equation. So we have to somehow discretize it. So you we have a few points like this. So this is the space in this, and this is the time. So we have to find a way, okay, to go from time step n to time step n plus 1. And so to get the velocity at the position I, okay, when you discretize, you have to take into account, presumably, these 3 points here. Okay, so you just write things in the most naive way you could, which is essentially writing the derivatives using the 2 neighbors here. Okay, so this is the most natural things you could do, but it turns out to be unstable. And the reason, it's because if you think to the problem with these equations here, if you say it's positive, all the information is coming towards the left, okay? And because you use to calculate your derivatives this point toward the right, it means that you are using information from a point which is unable physically to contribute to the signal at this point here. Okay, so your signal is not upwind in a sense. So this means that you have information which it's propagating unphysically. Okay, so in a sense it operates like a negative viscosity. So the system is unstable physically for that reason, and you can do the math of that. It's not difficult. So it's so-called Von-Neumann analysis. So the way it's done is you just take the Fourier transform. So you decompose your signal in modes like this. So you have the amplitude and the phase of each mode. And so you can simply calculate the amplitude of each of these modes at time n plus 1 as a function of the amplitude of the mode at times n, using the simple discretization that you infer. Okay, so it will depend on position n minus 1 and n plus 1, as we saw, which generate this exponential here. And so you can just do a quick calculation. It's not difficult. And then you can express the amplitude of your mode at times n plus 1 as a function of the amplitude at time n. Okay, and then you can calculate the module of this amplitude. And you see this number, whatever you do, whatever your choice here for the discretization parameters, will always be larger than 1. Okay, which means physically that as time goes on, your modes are amplified. Okay, whatever you do, and that's this is unstable. It means that you will get an exponential growth, and essentially you will quickly get an n. So it means that even if you have some noise in your flow, it's amplified, and that's it. Okay. So based on this physical consideration I was discussing before about how the information should be transported, you can then say, well, I want the informations to be purely upwind, okay? Which means that when I calculate the derivatives of that point, I should use not this one. I should use only the information that come from these two points here. So you can then rewrite your scheme in this way. So you say if A is positive, so if the information propagates that way, so I'm using these 2 points here, and if it's negative, I will use this 2-1. And then you can repeat the same analysis. Okay. So this time you do not have the exponential minus ek delta x that came from that term here. You just have this one. And so you again, you can calculate the module again. So the ratio, the module of the ratio of the mode amplitude at times n plus 1 and times n. So this is an easy calculation again. It is expressed here, okay? And this time you see that this ratio can be lower than 1, okay, because of the minus here, if you choose C adequately. So if C, which is called the so-called courant conditions, is smaller than 1, then you find that the modes, so the ratio of the amplitude is actually shrinking with time. So the noise is not amplified, and therefore your scheme is stable. Okay, so that's the origin of the current conditions. Of course, here we took a very simple equation, so just a simple advection equation, and then in this simple equation there is only one way to propagate information, which is just following the flow essentially at a constant velocity. If you have a more complex system, like a hydro system with sound waves, or like MHD system of equation, then you have many waves, or many 7 waves, say in the case of MHD. And it means that you have to do this kind of procedure wave by wave. So identifying all the modes that can transport energy, and then you must be sure that that the information for all mode will be upwind. Okay? But this could imply that you may have to actually discriminate between the different modes and do a procedure adapted for each mode. Okay? So that will be the essence of building stable and accurate solver. Okay? You have to play around with this concept of upwinding and trying to find the best way to be stable and accurate. Okay? So all the issue is there. Okay. Right. So let me now discuss a little bit more the standard MHD equation. Just a quick questions. Who has already run, say, MHD codes and or just been working with MHD equations? Okay. Right. Okay. So if I understand, most of the people in the room are not extra familiar with MHD equation. Is that the case? Okay. Thank you. Right. So so the MHD, I assume everybody is familiar with hydro equation. Okay. So the MHD equations differ from hydro equations through the Lorentz force. So this is the current, and I drop the 4 pi or the mu 0 or everything. Okay. So this is the current. So G cross B. Okay. And so this is essentially the Maxwell equations. Okay. So dTB equal minus curl of E, and E, if you do a Galilean transformation, is equal to V dot B, okay, which gives the Maxwell-Faraday equation if you are doing ideal MHD. And then you have the dB constraints, which in principle is a consequence of that equation, in the sense that if initially dB is 0, okay, through this equation, if you just take the curl of this equation, you find that dB, okay, all of that will drop. As you see, there is this can be rewritten as a curl. Okay, so if you take the divergence of these equations, this will be 0, So if dV is 0 initially, it will stay 0 as time goes on. I mean, this is what physics tells you, but then you have to teach your numerical methods to follow the physical law, in a sense. So you see there are so one new force, okay, and one new equation with, in a sense, a conserved quantity. You can see it that way. When you are dealing with MHD, with hydro, you want the mass to be conserved and say the momentum and the energy. Now you want also, on top of that, to have dV equals 0 and conserved. Okay, so this is what we want to do. So the G cross B force can be decomposed in two terms. One is the so-called, is similar to the pressure, it's the magnetic pressure, and that's typically if you have the field lines, okay, if my hand has the field lines, okay, if they come close together, there would be a force trying to reduce the magnetic gradient. And there is this force here, which essentially tells you that there is a kind of tension. There is some strong similarity with what you have in a string. Okay, if you try to bend the string, you will have a force like that. That's why it's called tension. And these terms is really the very reason why MHD is so different from hydro. Okay, it tells you essentially that if you do that, okay, in hydro you don't care too much. I mean, the two blobs of gas, there is no surface tension, and there will be no consequence, no restoring force. But if you do that in MHD, okay, essentially you will bend your field lines, okay, and at some stage it will stop. Okay, so there will be a restoring force trying to bring your fluid particles back, which means that this kind of flow, they have a memory in two directions. It's only if you go along the field line that there will be no restoring force. Okay, but along that direction of this one, okay, the flow is trying to react. Okay, so that's very different for that reasons with what you got in the hydro case. So these equations can be written, and that will be important for the finite volume methods, in a conservative way, which means the conserved quantity like the density and the divergence of a flux. So this is also true for the momentum, where you have the conserved quantity, which is the momentum, and the flux. Okay, so that's a typical aerodynamical flux, but you have also the G cross B force that can be written as a flux. And the same is true for the energy. This is actually the Poynting flux that I'm sure you are familiar with when we do the electrodynamics. There is the Poynting vector. So this can be written as B dot E essentially. So this is a Poynting flux. Right. And yeah, no, an important remark also for the conservation of dB. So here we have this conserved quantity and a divergence of a flux. When you look at the Maxwell Faraday equations, you see now you have the curl of the electric field. Okay, and you know that if you integrate the curl over a surface, you can, I mean, I will rediscuss that later, but it's probably worth being aware of that already at this stage. You can modify your integral and transform it into a contour integral. Okay. While if you have the divergence of a flux, you can transform your volume integral into a surface integral, okay, which tells you that you have flux going through or being exchanged between cells, okay. So there is a kind of slightly change of point of view between a volume conserved quantity into a surface conserved quantity. Okay, so here you typically have to integrate over a surface to get magnetic flux, and if you do that, you recover something similar to what you have for the standard hydro equation, which are conserved in volume. Okay, so this will also have an influence on the scheme that will be chosen, and the reason of the staggered mesh I described yesterday is rooted here. Okay, I will be discussing that tomorrow in more detail. Okay. So yeah, as I said, you can write this equation as a conserved quantity, the whole system as a conserved quantity plus a flux. Okay, this is done in 1D, and you can introduce the so-called Jacobian. So this matrix here, which will be also useful in the for the MHD solver. And so in 3D you have the generalization of with the free components. Okay. Right. So let me now just briefly describe the waves. So in MHD, so in hydro, in the similar situation, you will have essentially 3 waves when you have at an interface. You will have 1 sun waves propagating toward the left, 1 sun wave propagating toward the right, and you will have an entropy mode in between, which is also called contact discontinuity, which is not propagating, it is propagate at the velocity of the flow. Okay. In MHD, you have on total 7 waves. So you have 3 waves propagating toward the left, and 3 toward the right, and you still have the entropy waves. So the 3 waves are I mean, 2 of them are a kind of mixture between acoustic waves, so the classical sonic waves, and MHD waves, essentially based on the pressure. So the fast modes are obtained when the sun waves, or say the thermal pressure and the magnetic pressure, I would say, collaborate. So they just, so the 2 velocity, the sun speed and the Alphen speed add up. Okay, so that typically it's easy to understand. If you have a density, if you say the gas is isothermal, if you have a density peak, this is also a pressure peak. Okay, so that tends to spread out. If your density peak is correlated with a magnetic pressure peak, okay, you have to take into account not only the thermal pressure, but also the magnetic pressure. Okay, and therefore, by this simple argument, you see that the typical fluid velocity will be a quadratic sum of the of the sound speed and the Alphen speed. Okay, so then the modes propagate faster than if you had only thermal support. So the waves propagate faster, so those are called the fast magnetosonic modes. Okay, things add up. But then you can also have situations where instead of having a peak of magnetic field where you have a peak of say density, you have now a whole of magnetic field. So the density and the magnetic field can be anti-correlated. The physics does not prevent that. You can choose freely the magnetic field. And you can even have situation where the magnetic pressure will exactly compensate for the thermal pressure. Okay, if you write, say, your hydrodynamic equations, and if you are free to choose the magnetic flux or the magnetic field, you can easily solve the equation, and you can set up a magnetic field in such a way that the magnetic pressure plus the thermal pressure are constant, okay, or is constant. In that case, equilibrium, no propagation. So this is called a slow. Well, if there is no propagation, it's not a wave, okay. But in the general case where you are not exactly in equilibrium, you can easily see that the signal propagates less rapidly just because of this tendency to be closer to equilibrium. Okay, so the waves, so the slow waves, they propagate less rapidly than the sun waves because of that. Okay, so those are the two compressible modes that you find when you are dealing with MHD. But there is a new kind of mode which is based on the tension and which is similar to what you have on a string. Just because of the tension, you have now a force that tends to restore the motions in the transverse direction, as I was describing with the string that you bend. Okay, so the tension tries to be a restoring force, exactly like if you pinch or if you kick a string, we see waves propagating. You have the same effect with when you have MHD. So those are the Alven modes, and those are transverse modes. Okay, so totally different from the longitudinal modes that you have in a hydro system. And again, this is the reason why MHD is fundamentally different from hydro. That's because of the transverse mode, due to the restoring force, the restoring tension force. Okay. Right. So you fundamentally your system will present 7 waves, and so those are the. So you will have the Alphen waves, the Alphen speed. Okay. So the Alphen waves propagate at the Alphen speed. Then you have the fast and the slow modes. So their speed is given by this relation. So the plus is for the fast and the minus is for the slow, and the entropy mode. So just to summarize, if you have a kind of discontinuity, sort of Riemann problem with 2 states, what you expect is to have a sort of wave fan. So the signal propagating toward the left and toward the right. But instead of having only 3 sort of states, which corresponds to the 3 waves that you have in the hydro case, you have now 7. Okay, because you have 7 waves in the system. Okay, so this is your wave fan. So here you have the fast magnetosonic mode, which go faster. So you have 1 here and 1 here, 1 to on the left, 1 to the right. Okay. Then inside you have the Alphen mode, which is 1 is here and 1 is here. Okay. Then you have the slow acoustic modes, which propagates less rapidly than the Alphen mode. And finally, you have the entropy mode in between that does not propagate or propagate at the speed of the flow, depending on the picture you prefer. Okay. So 7 modes. Okay. 3 toward the left, 3 toward the right, and 1 that is passively affected by the flow. All right. Okay. So I'm going now to discuss a little more on the so-called Godunov method. So which are generic, I mean, it can be applied both for hydro and MHD. So originally this method was developed by Godunov, and it's well suited to deal with shock and discontinuity, so that's why they became popular in the field of astrophysics. So the idea is that you discretize the flow in cells, and your quantity represents the mean value of, say, the density, so within the cell. Okay, so you average, if this is the density, okay, you average your density within the cell, and this is what this point represents. Okay, that's more clearly expressed here, where you have this averaging being explicitly written here. Okay, so the quantity that you write here is the average value of this quantity through your cell. Okay, and so this is different from what we typically do in the standard finite difference method, where the point or the value represents the local value at this position. Okay, so here the value within the cell is the mean quantity. And so then the philosophy of the finite volume method is to say that because this is what you have here is the mean value, okay, you can exchange fluxes. So you have the mean density here, so this value times the volume is the mass, or the momentum, or the energy, the total quantity within the cell, and then you can exchange a flux. There is a flux between the two neighbors. So there is no when you do not have any derivative of the flow, you just have flux. And this is more clearly visible when you take the conservative form of the equation, where you have the time derivative of the quantity is equal to the divergence of a flux. Okay, so if you take the integral form of this, which is written here, I guess, you see when you write this way, you see there is no, strictly speaking, derivative. They are just conserved quantity and flux being exchanged between the cells. So this means that you avoid the problem that you encounter when you deal with finite difference methods, which is having extremely stiff derivatives when, for example, you have a shock. Here you don't do with derivatives. You just have flux. So everything is smooth for that reason. And so when you discretize your flow, the variable at time delta t is the variable at time, say, 0 plus the flux, okay, being averaged over the surface and being averaged in time. Okay, so this is the quantity which is written here. So it's important to realize that the flux are always, wrong, or say not exact, say, because it's numeric. Okay, so you are not solving the equation exactly. But the important issue here is that even if your flux are slightly wrong, and as always, they are always slightly wrong when you do numerics, it's not a big catastrophe, because by construction, since you exchange the flux between cells, you will still conserve mass, momentum, and energy exactly. Okay, so this kind of scheme have this nice property to conserve the quantity that should be conserved by construction, because you take something to a cell and you give it exactly the same amount to the other cell by construction, even if your flux are slightly wrong. Okay. Right, so to apply this method, which again is just based on the conservative form of the hydro or MHD equations, we need now to deal with interface. Okay, so we have essentially a cell at the left, a cell on the right, and we need to calculate the flux in between. So that's called the Riemann problem. So as you will see, this is in general, okay, a difficult problem, and the aim of the following will be precisely to try to understand, to find methods to compute this flux. Okay. Well, first, I'm not going to describe them exactly, but I wanted to mention. So there is actually a procedure in the hydro case to iteratively find the solution, the exact solution of your Riemann problem. So there is a small algorithms which have been developed, and so essentially you find what I just showed yesterday. So you find the three waves. Okay, so one is in that case one would be the shock, one will be these rarefaction waves, and the last one, the contact discontinuity is there. Okay, so once you solve this pattern, you can calculate exactly the flux that it implies, and therefore you can solve exactly the Riemann problem. Okay, so this is this exact Riemann solver are implemented in many hydro codes, and they can be used. But they are because you need iteration. Usually they are a bit expensive, so it's interesting to have cheaper solvers. And also, more fundamentally, maybe in the MHD case, no exact solver is known. Even so, it would be very expensive. And the reason is that there are many cases in MHD, so many configurations. So we need to find approximate solvers that can allow us to find the flux. Okay. So I will first discuss the so-called raw type of solver, which are linearized solver, which have been developed for this sort of hyperbolic system. So let's again consider our simple advection equation like this. So if you have two states, left state and the right state at the beginning, okay, so essentially left and right here, as time goes on, the systems, so your left state propagate toward the right, okay. So in this case, the solution of the problem is very simple. So if you have time here and x here, so the left state propagates towards the right state. Okay, so depending where you are in time and in position, you may either be on the right state, either on the left state, depending of the time. As time goes on, you will always, the left state will always reach the point, the point you are considering. Okay. So this is the simple solution of that problem. Now, if you deal with a more complex system, which are not only one variables, but many, more than one, then essentially the advection equation becomes can be written with a matrix A, which is the Jacobian matrix, and the idea would be the same, except that now you have to, because this matrix usually is not purely diagonal. If it's purely diagonal, okay, then it's easy. It's the same. Each state will be represented, will have its own velocity in a sense. Okay, so we'll just have a linear combination of the various eigenvectors. So the idea is that in the general case where A is not diagonal, you will diagonalize it, okay, to find the eigenvector, eigenvalue of that problem. So you will decompose your system using the eigenvector of this matrix, and in this system you are essentially back to the simple case I just described in the previous slides. And so at the end, if you write everything using this base of eigenvector, it's just a linear combination of what you have on all eigenvectors. Okay, so typically you have lambda, which is the diagonal matrix. So K are the eigenvectors. So you can write your Jacobian using this decomposition. Okay, and then so your system U, your state U, can be decomposed onto this base of eigenvector. And so the left state is determined by this alpha coefficient onto the eigenvector, and the right states will be described by these beta parameters. Okay, so you have alpha coordinates for the left state and beta coordinates for the right states. And so working on this basis, you are back to the simple problem we described at the previous slide for each state. Okay, so if you just consider one of them, one of the eigenvalue and eigenvector, say this one. So if say if x is negative, then the left state, which corresponds to this eigenvector, is the one of the corresponds to the left state. And if x positive, then you switch from alpha to beta because you have been invaded by the left state. Okay. So what you have at the end, okay, is a mere linear superposition of the two systems, and as time goes on, okay, you sort of mixed, okay, more and more linearly, simply the left and the right state, okay, depending on the value of the wave speed. Okay, it's not difficult. I mean, you just have to write this for yourself, but this is simple linear analysis. Okay. So using that now, you can actually calculate the flux to which it corresponds. So you want to know what you have at the interface. So in 0, okay, at this position here. And so you just write your state at 0 using, as I was saying, the left component of the eigenvector which are propagating toward the right, and the beta component of the eigenvector which are propagating toward the left. Okay, so for each contribution, you take your state at 0 is a linear combination of the signal that propagates toward the left and the signal that propagates toward the right. Okay, so just a mere linear superposition. You just have to pick up the states which have been propagating toward the left or the right. So you get this linear combination. And then the interesting thing is that you can rewrite this configuration here. You can express it if you add here, if you add and subtract the components which are missing here to create the left state, so you have to add the component from 1 to I, to capital I, okay, and then you subtract them. So here they have been subtracted, and here they have been added, and when you add it, then you find the left state, okay. So you can write this state at 0 as the left state plus this sum, or you can write it as the right state minus this sum, or you can take the average value of these two quantities because they are equal. So when you do that, you get the average value of the left and the right plus a correction, okay, which is the difference between your the two states you had initially. Okay, and then because it's a linear system, if you want to take the flux, you just apply the Jacobian to the state at the interface, U0, and so when you do that, you just get A, so the Jacobian stamps the left value here, which give you the flux on the left, the Jacobians to the right, which give you the flux to the right, plus these terms here, where you apply the Jacobian to the ky, which is an eigenvector of the Jacobian by definition. That gives you ky times the speed of, the eigenvalue, which is the speed of the signal. And then you get this formula, which is the average of the flux toward the left and toward the right, plus the terms which entails essentially the difference between the left and the right state times the wave speed of your signal. And this is very important. This is this is again very generic. And coming back to what I said previously, what we have been doing here, if you remember the very first slide of the lecture, the first choice, the first naive choice we took was to say, okay, I'm going to use the left and the right point to try to calculate the derivative, and we find it to be unstable. So that's what is done here. If you do not pay attention and just take the average, you would get with that, which is the mean flux. And then you see that by doing this procedure that I just described, we end up with a result which is taking the average of the flux, left and right, plus correction terms, which will, in a sort, correct, in a sense, this flux in order to ensure that your scheme is actually stable, that your information is properly upwinded. And the reason of that is because we have taken the eigenvalues of this matrix and taken into account each time carefully the directions to which the signals propagate wave by waves, or state by state, if you want. Okay? So you see the important structure here is this one, and this will be very generic. It will be recovered for almost all solver. Okay, you have a combination of the flux of the left and the right, okay, and the terms, okay, which typically entails the wave speed and the difference between your two states. Okay, so the exact dependence of, say, the coefficients here and those coefficients will vary from one solver to another. Okay, but the underlying ideas will always be the same. Okay, one essentially average value and terms which will be there in a sense to guarantee the stability of your scheme. But as you see, the difference between the two is like a gradient. So if you think now in terms of fluid equation, so the conservative fluid equation, you have a conserved quantity, the time derivative of a conserved quantity, and the divergence of a flux. So here you have the divergence of essentially a gradient. So this is a kind of second order scheme, or second order terms. It's a viscosity, in a sense. So by doing this, you may think, one way to think to that problem is that you have to add the proper viscosity, okay, for your scheme to be stable. And here, in this particular case, you do this, as I said, wave by waves. Okay, so you have here the scheme, which is probably the most accurate, and which is just at the verge to be stable, in a sense. Okay, so with less dissipation, if you would be reducing one of these wavelengths or one of the wave speeds, sorry, you would get something that would be unstable, because you would have some. You will not be purely upwind. Okay? You will have some signals coming from, propagating unphysically in the system. Okay, so it's a bit technical, but it's not difficult. So if you are interested by doing this, I would encourage you to just write this equation by yourself. It's kind of straightforward. Okay. So the message now I would like you to get is this one, essentially. Okay, all solvers are constructed that way. Okay, with a sort of average of the left and the right fluxes, which would be unstable. But then you add some upwinding terms, which can be seen as kind of viscosity, if you want, which will make your scheme stable. Okay, and you do that wave by waves. Okay. I had an example, but I think I'm skipping it. Okay, I've been very slow. So, I will give some more details on the Rho solver. Maybe I will be quick, but so the idea of the Rho solver is to use this description. So the underlying idea is that when you write, so your equation, as I said, you can formulate it that way. So using this Jacobian, which generally is a nonlinear system, and so the idea behind the Rho solver is to say that solving the system in the nonlinear case, okay, it's too difficult. We don't know how to do that. So the idea is to replace this nonlinear Jacobian by a linear one, which then will be easy to solve by the method I just described. Okay, because everything can be transposed if it's linear by what I just said. So you are replacing a nonlinear matrix by a linear one, and all the game of the Rho solver is to find a matrix, a linear matrix, which has the good properties. Okay, and then how good? This is the question. So we would like, just quickly, just to give you a flavor, we would like this sort of matrix, okay, to first to have some good properties. So first one, we would like this matrix to have so m eigenvalues and m eigenvector, which sort of preserve the wave structures of the problem. Okay, so this is called the hyperbolicity. Then we would like that if your left state and your right state are identical, we would like the linear matrix to be exactly equal to the nonlinear one. This is called consistency. And then the most difficult to satisfy is actually this one. So we would like that the matrix times the difference between the air and left state is equal to the flux difference. And these properties guarantee that you will recover exactly the isolated discontinuity. So when, for example, you have a shock, which is a stationary shock, this is an isolated discontinuity. It will stay like this. There will be no evolution of the state. So the continuity is purely isolated. And so you would like your solver to also reproduce the same sort of to be able to deal properly with this isolated discontinuity like shocks and so on. So I'm not. I think I will not give more detail. I just wanted to give a flavor. So there are ways to actually construct this matrix, and at the end you will end up with a Jacobian, which is so with the matrix A, which will depend on the average quantity between the left and the right states. So if you look, for example, to RAMSES or to Athena, you will find this row solver being implemented. You will see it's quite a lengthy routine with a complex, it's quite complex. So you have a set of left state, right state, and so on. So to really code that, you have to understand exactly what's going on. So you have to read the papers, the methodology papers very carefully, and then to check that you have not been doing any mistake in the implementation. Okay, so I think I said enough on the row solver. Once again, what I think is interesting at this stage for you is to catch the philosophy of this row method. So it's essentially wave by waves. Linear procedure. So you linearize in a sense your problem. You replace your nonlinear problem by a linear problem, which has the good properties. And then you decompose your linear matrix on the eigenvectors, and then you solve your system wave by waves, as I was describing. Okay. So you guarantee that the information propagated by each MHD waves is upwind, but this is done really on a wave-by-wave basis. Okay, so each waves, or the information carried by each wave, is upwind. Okay. So just more practical consideration. So the row solver works reasonably well, and they are probably the most accurate because they are really very close to the physics of the system. So they are widely used, and they very often serve as reference. The problem is because they are linear, when you have a very strong nonlinearity, like a strong shock, usually they will do very badly, and they can crash. So you can have something like rarefaction shocks, for example, where the entropy will not be violated. So very often there are switches implemented. So when you detect that, say the gradients are too big or something like that, you will switch locally to another method, which will be more diffusive, as I will describe later, but also more robust. Okay, so that's typically the kind of switch you will find in many codes. Okay. So I'm going now to start describing a little bit more the so-called HLL solver, which, as I said, are the ones which tend to be used. And for that, I just need to remind the result, maybe. When you have a shock, I mean, you know that the flux is conserved through the shock. But this is true in the frame of the shock. Okay. If you are not in the frame of the shock, so which is the case typically when you have solving your equations in the grid, the velocity of the, I mean, you are working in a sense in the lab frame if you want. Okay, so at each interface, if you have a shock at an interface, you are not going to work in the frame of the shock. You are going to work in the frame of your grid. So this means that the so-called Rankine-Monod conditions has to be modified, and the way it's done, it works is that this relation now entails the local velocity of your discontinuity, so the velocity of the shock. So you have to take into account these two terms, so the local velocity times the left state and the right state. So you can see this by writing this equation. I'm skipping that for now to go slightly faster. And I'm starting to describe this so-called HLL solver, which is the simplest of this type of solver. So the idea is that, so previously in the row type of approach, the philosophy was to try to simplify, okay, the problem in a sense, to linearize it, but to keep the wave structures and to solve all waves. Okay. Now the philosophy is different. You say, okay, this wave fan is a mess. It's too complicated. I'm not going to solve it. I'm replacing all of that, all of, you see, the various jump and waves by a single state that I call the star state. So I have waves propagating toward the left and the wave propagating toward the right. So those are the two fastest waves in the problem. And I'm not attempting to resolve the inner structure of that. I'm just trying to find a unique star state that's going to sort of be a kind of average. Okay. And from that, I try to obtain a flux. Okay, so you see slightly different philosophy. So in a sense, to make the link with what I just said before, that would be, okay, saying this is too complicated. Okay, so I'm going to replace all these waves velocity by the fastest one, because if I take the fastest one, I will guarantee my signal to be upwind. Okay, but I will also be more diffusive. Okay, so less accurate. Okay, so it turns out that this star state can be easily calculated using simple conservative laws. And that can be done following the procedure. So you have your left state, okay, and your right state separated by an interface like this, okay, and you have, so at time 0, so everything is left and right, and as time goes on, your fastest waves propagate toward the left, and your another fastest wave propagate toward the right. So your sort of star state is sort of invading the interface, propagating toward the left and right. So the idea is to say, okay, I'm going to do a simple balance, and I'm going to take a volume of control to just calculate, using conservative laws, to calculate the quantities. Okay, so this is my volume of control. Okay, and I'm just going to use the conservative form of the equation. So at time 0, if I integrate over that system, okay, the total quantity of U, say the density, for example, that would give me the mass, would be the surface I have here, okay, times the length, this length here, and times UL and U right. Okay, so this is integration here and here. And then at times t, I can estimate the total mass, say, as I have in the system, in my volume of control, either by counting using the flux, which have passed through the left and the right interface. So in that case, I will say that what I have at time t in my system is what I had at time 0 plus what enters minus what leaves the system. Just a standard conservative form. But I can also say what I have at the system at times t, okay, is what I will obtain through a spatial integration. So what I have now is this plus this plus this. So this is what is written here, okay, given that lambda L is negative. So this is this volume here times the quantity times the left quantity plus what I have here, what remains here, okay, which is the right state times the volume which is left here, and plus the contribution to the star state, okay, which is then written here. So this is the volume occupied by the star states times the star states. Okay, so because the system is conservative, I have now an equation that will link the star states to the left and right flux and left and right states, as well as the left and right wave speed. Okay, it's a very simple equation. You just say time, just make a time integration and a space integration, and things are equal. So that gives you the star state here, written as I say, it depends on the left and the right flux, left and right states, and as well as the left and right wave speed. Okay. Now you want to, what you are interested in is not the star state itself. What you want is the flux, which is exchanged at the interface. Okay, so let's do another mass integration, or let's use again the conservation properties. So for that, we again consider a volume of control. By this time, the volume of control will be between, say, minus L and 0. So just to come back to the previous slides. So we had a volume of control here, and now the new volume of control is between this position and this one. Okay, so we repeat the same procedure, But instead of doing that between these 2 points, we do that between these 2 points here. And so we do that again. And the difference is that now we know the start state from the previous integration. So now what we are looking for is the flux at the interface. So the variable now is the flux at the unknown variable is the flux at the interface, and the state is known. So again, writing, performing the time integration or the spatial integration, we repeat the same procedure, and this time we get the so-called star flux, so at the interface, as a function of the left flux and the star quantity minus the left quantity. And because we know the star quantity from the previous integration, we can replace it, and then we arrive to this formula, which is the so-called HLL flux. And you see it's the left flux times the right times the speed of the right waves plus the right flux times the speed of the left waves, okay, plus the difference between the two states. So it's similar to what we inferred previously from the linear analysis. If you look back to this flux, okay, you see previously we had the average, okay, plus difference between the two states. I should stop now. Okay.
You should. Yeah, you're 15 minutes over.
Okay, so just 5 maybe. So now we have a different weighting. Okay. The two flux here I weighted not by the average, but taking into account the wave speed. Okay, and we still have terms like this one, which take into account the difference between the right and the left states, and which I repeat can be seen, if you want, as a diffusion that will ensure the stability of your scheme. Okay, so it's a different weighting of the same quantities, essentially. Okay, by doing this, there is an interesting property that comes up. If you are dealing with a supersonic system, okay, so if all the information, essentially when you are supersonic, all the informations come from a single direction, this formula here, okay, will shrink to this. So to the left, pure left states. And if you are supersonic but coming from the other direction, then your flux will become equal to the right flux only. So in the sort of subsonic case, you will have a mixture between these two flux. And as, say, lambda L goes progressively to 0, okay, 0 means that you are just transonic, so your system is just becoming, say, supersonic if you want. So in this case, lambda L over lambda L, I mean, obviously leads to 1. Lambda L drops to 0. So you are exactly recovering this value here. So you are continuously going from subsonic, so a mixture of flux and state, to something supersonic that depends only on the information that comes from the left or from the right. Okay? So the final state of HLL is actually to estimate the wave speed, because so far they have been assumed. And so here again, various propositions have been done. It turns out that simple estimate, like just taking the fastest wave speed toward the left, or to the right would work. So that's typically what is done. You have more, elaborated considerations, like taking, for example, the waves given by the row solver, for example. Generally speaking, this scheme is robust. Okay, it has been proved to guarantee the positivity, which means that you should not get any negative pressure or density. It is, however, a bit unstable. A bit approximative, so a bit diffusive, because you have not been dealing with the detail of what's happened at the interface, and it's sort of this average procedure of taking just a single star state is a bit simplified, and for that reason the scheme is a bit diffusive. Okay, and so tomorrow I will discuss in more detail, say the more accurate HLL scheme which have been developed, and I will finish with this HLL-D scheme, which again is the one that you will probably find in most codes available on the market, because it's the most, say, accurate and robust solver we have at the moment. There is another one written by a mathematician, but it's orders of magnitude more complex than what I showed before, so I will not enter in that game. So thank you for your attention.